Okay, in this PowerPoint presentation, we're going to go over chi-square, and it's not chi-square or chi-square. In statistics, we pronounce it chi-square. We're going to go over two different types of chi-square analysis. So the first one is the chi-square goodness of fit, and then we're going to talk about chi-square test for independence. Okay, so let's talk a bit about what non-parametric, which is what a chi-square is, versus parametric. So the hypothesis test used thus far, or what we've been using so far, is talking about more like population parameters. And so we also call these parametric tests. And some of the assumptions they all share is that we're pulling our distribution from a normal distribution. And the different samples have met this homogeneity and variance assumption. And there's a numerical score for each individual. Shifting just a little bit with non-parametric tests, we need to have these whenever we don't necessarily meet all of those parametric test assumptions, right? So maybe we're pulling it from a distribution that's not normally distributed or violates that homogeneity and variance assumption. Or maybe the thing we're looking for, the data we're looking for, isn't necessarily a numerical score. Okay, we're going to use non-parametric tests. And again, with parametric tests, you can use ordinal scale, interval scale, or ratio scale. And some of the examples of an ordinal scale, this is all the kind of data that's ranked according to whether they possess more or less of something. You can have it be like, oh, low ability versus medium ability versus, high ability. The interval scale is data that possesses equal intervals between each adjacent units, but doesn't necessarily have an absolute 0 point. Right, with this one you can have, like, if you're measuring average temperature, right? In Nome, Alaska, you're going to have some negative numbers. That's okay with interval scales. Last one, ratio scale, data that possesses equal intervals, just like the interval scale, but has an absolute 0 point, right? No matter how much you diet, you can't weigh negative 12 pounds. And same thing with age, right? The second you're born, you're in a positive number. You can never be negative 12 years old. With non-parametric tests, we rely more on those nominal scale data, right? So yeah, this example here is maybe the political party that person is, right? Republican versus Democrat versus Independent versus Green Party versus Libertarian versus whatever. They're not necessarily better or worse, they're just different, right? The Democrats don't out political party independence, they're just different political parties. Okay, so chi-square and any of the other non-parametric tests, you don't necessarily state a hypothesis in terms of specific population parameters because you might not have population parameters. And again, you're going to make a lot less assumptions about the population that a sample was pulled from. Okay? And so non-parametric tests, you're also going to hear them referred to as distribution-free tests. And participants are usually classified into two categories, right? And again, we're going to rely more on nominal or ordinal scales. Okay? And a little bit something different too with non-parametric tests, the data that we're looking for are more frequencies or counts versus absolute magnitude of a certain variable. So null-hypothesis, and again, there's a couple different types of chi-square analysis. We're going to look at the chi-square goodness of fit first. Specifies proportion or percentage of the population in each category. And the null hypothesis would say something like, well, there's no preference among the categories. There's no difference in one population from the proportion in a different population. And again, we're going to rely more on frequency. So if I'm looking at different hair color in a class, right, I can say, okay, raise your hand if you have blonde hair, and like 2 people raise their hand, and raise your hand if you have brown hair, and maybe 5 people raise their hand, and raise your hand if you have red hair, right? So 1 person raise their hand. What we're talking about here is frequency or counts, okay? And we're going to notate that with FO, observed frequencies or frequency observed. And each individual is only counted 1 time in one category. So if I raise my hand for redhead, because I'm a redhead, I can't raise my hand later and say, oh, yeah, I'm blonde too. No, and again, there's no preference. It doesn't matter if you have red hair, blonde hair, gray hair, no hair, right? There's no good, better, best here. It's just what color hair do you have? Blondes don't out hair gray hair. They're just different color hair. But you can't be blonde and gray. You can't be bald and brown hair, right? The goodness of fit test compares the frequency observed, with the assumptions made in that null hypothesis. Okay? So what we're going to try to do is we're going to try to create what would we expect the frequencies to be, and then compare it to the frequency observed. And the expected frequency is symbolized with F, and then it's got a little E down there. It's the frequency value that's predicted from that null hypothesis and the sample size. And ideally, we would have a hypothetical sample distribution. Okay, some of our symbols. So chi-square is symboled by an x, and how you do the chi-square x is you have a straight line going right here, and then you have like a curly part of it right there. That's chi, and then squared, because it's called a chi-square test, so a 2 up there. And this is the lowercase Greek letter for chi. And the FO is frequency observed, and again, FE is the frequency expected. This is your first statistic for chi-square, and the chi-square goodness of fit and chi-square test for independence, which again we'll cover in both in this lecture, have the same equation. So this chi-square equals sum of FO minus FE squared divided by FE. That's the same for both those types of analysis. Okay, so here we have a frequency distribution, and we're going to do eye color. So you can say you either have blue eyes, brown eyes, green eyes, or other. So over on the far left-hand side, we have a bar graph, not a histogram, right? Because we're talking about discrete or categorical variables. And then we have the frequency distribution table there. So we have 12 people have blue eyes, and 21 people have brown eyes, and 3 people have green eyes, and 4 people have other. Okay, so we're going to get a sample of 40 people, and we're going to see if there is a preference for eye color. So biologists, geneticists love chi-square for this type of reason, because they can kind of see, okay, is one more dominant than the other? Because if there was no dominance, then we should see the exact same number of brown eyes as blue eyes, as green eyes, as purple eyes, as pink eyes, right? And there would be no dominance of that. But as we'll kind of see right here, there is a dominance. So how you compute this chi-square goodness of fit is first you're going to determine the frequency we would expect each cell would hold if the sampling is random from the null hypothesis population. So again, we started with 40 people. If we have 4 categories, well, then I should assume, if there's no preference, if there's no dominance, that I should have 10 blue, 10 brown, 10 green, and 10 other. Okay? So this would be our FE, our expected frequency, again, if that null hypothesis is true. But we can tell here that the frequency observed is different than the frequency expected. Instead of just having 10 people with blue eyes, we actually have 12. Instead of just having 10 brown eyes, we have 21 people with brown eyes. It dips a little for green and others, so we should have 10, again, if there's no preference for people to have green eyes, but we only had 3. And the same thing for other, right? So these are our people with maybe hazel eyes or purple eyes, what do they call that? Alexandrites, right? Or pink eyes for albinos, right? So with this one, we should have 10 again, but we only have 4. So FE is frequency expected, FO is frequency observed in that sample. Okay, so let's get into some math. So again, our chi-square statistic, or our chi-square obtained, is sum of FO minus FE squared divided by FE. Okay? And we just start pulling in numbers. So where did I get this 12 right here? Well, I got that my frequency observed of my blue-eyed people minus my frequency expected for blue-eyed people squared divided by 10, our number for that one category of blue. Okay, same thing for here for brown. So my 10 is my frequency expected, but 21 is my frequency observed. I take 21 minus 10 and square that, and then divide by 10. I'm going to do that for each one of the categories. So I have my blue eyes here, my brown eyes here, my green eyes here, and all my other different color eyeballs right there. And I get a chi-square obtained of 21. And I know that you think that's kind of high, but it's going to be okay. I'll teach you how to do chi-square crit, or critical value of chi-square. And just like in all the other ones, we're going to compare chi-square crit with chi-square obtained and see if it falls in that critical region. So how we find the critical value of chi-square is categories minus 1 is our degrees of freedom, right? And when you can use the table, or you can find the table for chi-square in your textbook or online. And I even have a video that shows you how to find your chi-square crit. And if I'm going to use alpha level 0.05, and I have 3 degrees of freedom, my chi-square crit, or my critical value of chi, is 7.815. My chi-square obtained is 21. So I would reject that null hypothesis. APA-wise, right, and just kind of read along with this. It says, this researcher ran a chi-square analysis with 3 degrees of freedom, so they had 4 categories, and they had 40 people in their study, gave them a test statistic of 21, the p-value being less than 0.05, so we rejected the null hypothesis. And then you kind of have to pull back a little bit and say, okay, what were our high and low watermarks? Well, brown eyes was observed the most, and green eyes the least. So a biologist or a geneticist could then tell, well, maybe there is a preference for brown eyes. Maybe there is a dominance, right? That if 2 genes are presented, the brown eye gene is going to dominate over maybe a blue eye or green eye or hazel eye. And green eyes are maybe a little bit more recessive. The null hypothesis should be retained if the discrepancy between the observed and the expected values are small, right? So if I would have gotten like, well, 10 blue eyes and 11 brown eyes and 9 green eyes and 10 other eyes, then we wouldn't reject the null hypothesis. Yeah, there's a little bit of difference, but the discrepancy wasn't that big. Now, the discrepancy was large, and so we rejected the null hypothesis. And chi-square distribution includes values for all possible random samples when that null hypothesis is true. And just like we did with f being kind of like a t-squared, anything you square is a positive, so all chi-square values are also going to be in the positive range. You can never get a chi-square obtained of -2 or -12. Chi-squares are family distributions, and the distributions determined by the degrees of freedom. And again, the degrees of freedom for chi-square goodness of fit is categories -1, or DF equals C -1. And from that, you can find your critical values of chi-square. Switching gears just a little bit. So up until now, we've been talking about the chi-square goodness of fit. But now I'm going to show you how to run a chi-square test for independence analysis. And this is when there's a relationship that happens on 2 different variables or 2 different levels. And it can be definitely more than 2, but at least 2 by 2. Okay? And again, each individual is classified on each variable. And we're looking at the counts or the frequency presented in each one of those cells. The research may be experimental or non-experimental or quasi-experimental. That's all okay. And again, the frequency observed for the sample is used to evaluate the relationship between those 2 variables in the entire population. So again, we're looking at a sample and trying to use that over to a larger population. Okay, so this is a simple 2 by 2 matrix, meaning I have 2 categories up here I can qualify for, and I have 2 categories over here on the left-hand side I can qualify for. Okay, so maybe they're saying the hypothesis is, or the research question asks, I wonder if there's a relationship between how many kids somebody has and their education level. So again, we're looking at them on 2 different variables. 1, what's their education level attainment, and 2, how many children do they have? Okay. So to be in cell 1, I would have to say yes, I have a college education, so that gets me in this row right here, and I have 2 or less kids. And that is true for me, right? So I have 2 kids, and I'm college educated. So I'm in this cell, we call it. And there's 53 other people in this cell, or 52 other people with me in this cell. Okay. But what if I had a college education, but I have, 4 kids, 10 kids, right? So more than 2 kids. Well, then the numbers kind of drop a little bit, right? So there's only 22 people in this study that can say they have more than 2 kids and are college educated. Now, that's what happens down here. So down here is the high school education only, right? So if you only have a high school education and you only have 0, 1, or 2 children, you can be in this cell number 3. Okay? But if you have a high school education and you have more than 2 kids, then you'd be in this cell. Okay, so you can only qualify to be in one cell. You can't say, I'm college educated and I have 2 or less kids. And I'm high school educated only and I have more than 2 kids. No, you got to pick one cell. Now, this isn't limited to 2 by 2. All right, I'm just showing you the 2 by 2 because it could be no kids, 1 or 2 kids, and we can have a third column over here, 3 or 4 kids, right, all the way to like 9 or 10 kids, right, and keep going. Same thing over here. I can say no high school education, high school only, college or your undergrad only, master's, doctoral. I can keep going, right? So I can have like a 5 by 10 if I wanted to. Okay, the numbers here, 53 and 22, add up to the marginal row total, right? So, because what this is asking is, regardless of how many kids you have, do you have a college education? Same thing down here. Regardless of how many kids you have, add these two numbers together, 37, 38. That is your education level. Same thing here. Now, regardless of education level, if you have 0, 1, or 2 kids, is over here. So we're going to call this one right here a row if it goes left to right, and up and down is column. Okay. This number down here in the bottom right-hand corner is everybody all together. It's like our N, big N, if you want to think of it like that. Okay. The null hypothesis for a chi-square analysis test of independence is there is no contingency relationship between the variables in the population. And again, depending on if it's a 2 by 2 or a 3 by 3 contingency table, the null hypothesis would say, well, the variables are independent, right? There's no consistent, predictable relationship between them. So the proportion of children for parents with a college education is equal to the proportion of children for parents with just a high school only education. There's no contingency or no relationship between those two variables. The frequencies in the sample are then observed, so we're going to have the frequency observed. And the expected frequencies are based on the null hypothesis of the same proportion in each category. So we're not just going to split them up equally. Now it has to be equal proportionally. Okay. The frequency is computed by the same method for each cell. Okay, so the frequency for each cell has to be the frequency in the columns times the frequency in the rows divided by n, capital N. It's like our big number for everybody in our sample. I think it was like 150 or something like that. So again, FC is the frequency for the total in that column, and FR is the frequency for the total in that row. N, big N, is the total number of frequencies in the entire study. Okay. So to find the frequency expected, and that's going to be the number in the parentheses, right? Now, the frequency observed is just how people raise their hand. Raise your hand if you have a college education and you have 2 or less kids. This is my frequency expected. Now, again, you see how it's not equal. We have 45 and 45, 30 and 30, because they're equal proportionally. This is how I'm finding it down here. I take my 90, right, the number in my column there, the total number of column, times 75, the row in my margin, divided by 150, the total number of people in my study. And I get 45. And I'm going to do that for each one of the different cells, right? So cell 1, cell 2, cell 3, and cell 4. Now again, if you're running a chi-square analysis on something that has a lot of different variables, then you have to keep running it for each cell, right? Because each cell has to have a frequency observed and a frequency expected because we're comparing that. Same equation. So it's the same equation as the chi-square goodness of fit. Here's your chi-square statistics. So chi-square equals sum of frequency observed minus frequency expected squared divided by frequency expected. The degrees of freedom are a little bit different. So now my degrees of freedom are row minus 1 times column minus 1. Okay, so here's my frequency or my chi-square obtained. So I take frequency observed, 53, because this was my college educated and 0, 1, or 2 kids, minus my frequency expected, proportional leveling out, right, 45, squared divided by my frequency expected, 45. And I'm going to do that for each one of the categories. So 1, 2, 3, and 4. And then I just sum them up. I add them up. So my chi-square obtained statistic is 7.07. Get out your table again, because again, we're going to need to find out our critical value of chi-square, and we do that with degrees of freedom. So row minus 1 times column minus 1, and gives me a chi-square crit, as long as I have alpha set at 0.05, and everything's one tail, right, because it's always positive skewed. 3.841, so we can reject the null hypothesis. Effect size, right, so this is row, this is what she looks like, right, she has it's almost like a slanty O with a line through it. Right? So what a chi-square hypothesis test is trying to do is it's trying to show that the differences did not occur by chance alone, that something is contingent on another thing. And they've done this study a lot, and the more educated, specifically females, the more education you have, the lower the number of children you have. So, and again, for a 2x2 matrix, which is what we just did, you can use a phi coefficient to measure that strength. How much does it dictate, or how much does it show that relationship between however much education I have and my family size? For larger matrices, 2x3, 3x9s, right, you have to use a Cramer's V. And again, Cramer's V and the phi coefficient, again, we're just trying to measure the effect size. And so for Cramer's V, you're going to go square root of the chi-square divided by n times the degrees of freedom, and you use the smaller of the row minus 1 divided or the column minus 1. Okay. Some of the assumptions: each observed frequency is generated by a different individual. And you really shouldn't be running a chi-square if you expect to have any frequency of any cell less than 5. Right, so this is best worked with larger numbers, larger sample sizes. Chi-square and Pearson correlation, right? Both evaluate the relationship between two variables, right? And they're going to try to use this data obtained to, what kind of data we're going to use is what kind of tests we're going to run. Right? Because if we're dealing with more nominal data, it's definitely more chi-square. If you're dealing with more interval ratio data, use the Pearson's R. And chi-square can evaluate the significance. Okay. As always, email me or call me with any questions. Get your homework done quicker and watch the videos. Thanks.